Now we're going to review what it takes to solve linear systems of equations. A system of equation is two or more equations that we need to solve together. So we need to find the solution that solves all of the equations together. We'll start out here with two linear equations and two unknowns. Usually we label them as x and y. And then our solution is an ordered pair, x comma y. The techniques that we will talk about for systems of two linear equations will be used when we talk about systems of three linear equations, which is ultimately our goal in this class. So we are focusing on linear systems, and for this lesson, our linear systems take the form ax plus by equals c. And we can see that in this first example and some of the subsequent examples below. Our first question, is the ordered pair 2, 1 a solution to the system? Since we are given an ordered pair and we want to know if it's a solution, we plug it in and see if it makes both of the equations true. So we'll plug in that ordered pair into both equations, and then we simplify and see if equations are true. 2 plus 2 does equal 4. 4 minus 1 does equal 3. Since that one ordered pair made both of the equations true when we plugged it in, then that ordered pair is a solution to the system. You try number 2 now. See if -1, -3 is a solution to this linear system. Pause the video, try it on your own, and then check. In this second equation, when we plug in -1, -3 into both of these equations, the ordered pair works for the first equation, but not for the second one. Since we want the one ordered pair to solve both equations at the same time, we say that it is not a solution to the system. For two variable systems, like what we're doing right now, we can graph these lines, because that's what they are, they're lines. We can graph them and see what the solution would be. Remember that a solution is an ordered pair that solves both equations, an ordered pair that's on both equations at the same time. So if we have this graph, and I will label it for you, so 2x plus y equals 0 is this blue one. I don't have a y-intercept. 2x plus y equals 0, so x and y being 0 would put me through that origin. And then x minus 2y equals 5 will be the black line. Notice also that if y is 0, x equals 5, so we have that x-intercept of 5 there. Now if I have these two lines graphed, how do I determine the solution of the system? What ordered pair solves both? Well, the ordered pair that solves both will be where those two lines intersect. And that ordered pair is 1, -2. I can check that very easily by plugging it into both of these equations. And I see that 1, -2 solves both of those equations. Therefore, that ordered pair solves the system. We'll take a look more about graphs in just a little bit. We can also consider tables. Here we have two equations. They're written in slope-intercept form here so that we can get y. So we have x along the top. X could be 1, 2, 3, or 4. And then each one of the lines for y is listed in a row. So for example, reading this table, if x is 1, then in the first line, y equals 4 minus x, y would be 3. So y equals 4 minus x. If I look at 1, 3, if I plug in 1, I will get 3, which matches that y coordinate, that y value. If I look at the second equation, y equals x minus 2. If x equals 1, 1 minus 2 will give me -1, which matches that y-coordinate. So notice that each row gives me the y-coordinate of the corresponding line for the given x-coordinate above. So I just have a list of 4 ordered pairs for each of these 2 lines. Clearing all of this away, the question becomes, identify the one solution that solves both equations. So I'm looking for one ordered pair that's the same for both equations. I see that the first ordered pair, if x equals 1, I get 2 different y values, so it won't be for x equals 1. Similarly, for x equals 2, I get 2 different y values. But take a look at x equals 3. Notice I have both y values equaling 1. That would mean that my solution would be 3. We can check this ordered pair in both of our equations. So we'll plug in y is 1, x is 3, 4 minus 3. 4 minus 3 is indeed 1, so that checks out. And then y equals x minus 2, x is 3, y is 1, 3 minus 2 is also 1, and that checks out. So we indeed have one solution that satisfies both equations. So whether it's the equations themselves, or a graph, or a table, we can use these different techniques to find the solution that solves the system. For linear systems with 2 variables, we can use any one of these 3 methods to find the solutions. We have graphing. We've already seen a graph of 2 lines and we found the intersection. So we could graph the lines and determine the intersection. The concern with graphing, though, is that we have to be precise with the graphing by using rulers and graph paper, and that can get pretty tricky. Also, if our solution isn't nice integer ordered pairs, then finding the values of the solution could be difficult. And that's why we turn to one of the other 2 methods to solve algebraically. So substitution and elimination are both algebraic methods for solving, which means we're using the equations themselves to try to solve for one of the variables and then find the other variable. Graphing is very visual. It's nice to see the picture. It also helps us if there are more than one solution or no solutions. But substitution and elimination allow us to get solutions that are not nice integers. For substitution, it's pretty much what it says. We're going to solve one equation for one variable and plug that expression into the other equation, so that we have one equation with one variable, we solve that, and then we go back and find the other variable. For elimination, we're using both of the equations at the same time to add them together or subtract them in such a way that we eliminate a variable. Let's talk about the number of solutions that we could have. When we have a graph, graphs are nice because, again, they show us visually what's going on. We have 3 different pictures, and we're going to state the number of solutions to each system. So in the first example, I have 2 lines, they cross, and they cross at exactly 1 point. So we have one solution for this first system. In the second graph, notice that those lines never cross. They're actually parallel, like train tracks. Parallel lines will never intersect. And since they will never intersect, there will never be one single ordered pair that solves both equations at the same time. And because of that, this system has no solution. And in the third picture, we have what looks like a single line. It turns out that that single line is really one line graphed directly on top of another. We have 2 equations that represent the exact same line. When we have this situation, every single ordered pair here is a solution to the system. Now, that does not mean that every single ordered pair in the plane is a solution to the system. Only the ordered pairs that are on that line. And since we have infinitely many ordered pairs on that line, we have infinitely many solutions to this system. You can't say that there's all real number solutions. We're talking about ordered pairs, x comma y. And it's not all real numbers for x and all real numbers for y, because this ordered pair way down here is not a solution to the system. So we have to be really careful with our infinitely many solutions. We will use that wording, and we're going to come up with an expression that will generate all of those ordered pairs for us. So now that we've talked about the 3 different situations that we can have when solving systems of 2 equations, in the next lesson, we'll show how to do each of those solving methods on some problems. And remember that all of this should be review, Algebra 1 type content. We need to refresh our memory on how to do the substitution and elimination for 2 variable systems, so that when we move to 3 variable systems, we'll have those skills to take that 3 variable system, reduce it to a 2 variable system, solve that, and then go get that 3rd variable, which is pretty much how we solve 3 variable systems. Unfortunately, in a 3 variable system, we're not going to have graphing. We can't graph in 3 dimensions by hand very easily at all. So we'll be looking primarily at that substitution and elimination as a combined method for solving systems of 3 variables.